Hi there, this is Yasser Walid, and in this video I will be presenting my final year project titled Development of a Solar Diesel Hybrid System for a Road Transport Application. It is known that our vehicles have been relying on fossil fuels for quite a long time, and they have been causing a lot of emissions that are harmful to our environment. This graph shows that transportation is the second most contributing sector to greenhouse emissions in Malaysia. It is also important to note that although electric and hybrid vehicles are emerging in the car industry, conventional vehicles are still expected to be around for a few more decades, and therefore it is important to find ways to reduce fuel consumption and the emissions cost. In conventional vehicles, the chemical energy stored in the fuel and oxygen gets converted to thermal energy during combustion in the engine, which is then transformed into mechanical energy that pushes the pistons in the engine. The vehicle gains the kinetic energy we seek for transportation as its velocity increases. But vehicles are usually equipped with various electrical components which require electrical energy. This energy is provided by the alternator on the vehicle, which is connected to the engine, and with the fast rotation it converts mechanical energy to electrical energy, which gets stored in the vehicle's battery. So this means that the electrical load also adds to the fuel consumption. Research students from the Vehicle Systems Engineering Lab at MGIIT in UTM have worked on something called RTES, Real-Time Emulsion System. It is a system which inserts water with the fuel to the engine, and this emulsion is meant to improve the fuel efficiency and reduce the emission of nitrogen oxides. From the several tests done on the RTES, it was noticed that the fuel saving without the electrical load can go up to 13%. However, when tested in a vehicle, RTES only achieved 2% fuel saving, since the electrical consumption of the RTES slightly increased the load on the engine. It can be concluded that if the electrical energy can be provided from a separate source, more fuel saving can be achieved. For this reason, using solar panels to supplement the RTES is considered in this study. The aim for this project is to utilize solar energy for the electrical loads on a conventional diesel-fueled vehicle in order to reduce the fuel consumption. And the objectives are first to determine the requirements for a PV system for a given vehicle and a given electrical load, which is RTES in this case. Then the sizing for each component in the PV system is to be determined. After that, we can analyze and discuss the results and determine whether the concept is feasible. For literature review, I will be giving a brief overview on two studies that are most relevant to this study. This paper was published in 2018 by researchers under the Joint Research Center in Italy. This paper presents a methodology to define the average productivity of PV panels on a vehicle and to quantify the resulting reduction of carbon dioxide emissions. The method relies on the analysis of a large dataset of vehicles' activity, which is acquired using GPS systems, combined with an assessment of the shading effect from physical obstacles and indoor parking. The results show that on average, the PV panels receive 58% of the available solar irradiance, making it possible to reduce carbon dioxide emissions from passenger cars in a range from 1% to 3%. In the second study, an experiment was made to compare the power output of a panel installed on a building and the panel that is installed on a vehicle. A route was designed in such a way that the vehicle went through roads with diverse characteristics, such as typical streets and avenues, areas with high and low car density, and zones with high and low buildings. In the middle is the radiation graph in the city of Arequipa. The graph on the right illustrates the comparison. The orange line represents the panel on the building, and the blue line represents the one on the vehicle. As you can see, the blue line drops to 0 frequently. This is whenever the vehicle is under shade. This interruption of the solar radiation caused a loss of around 19.6% of the power compared to the one on the building. For the methodology, I will explain the main steps taken to achieve the goal of this study. We will start by identifying the type and size of electrical load targeted, then the vehicle's specifications. Then we will evaluate the average daily solar irradiance in Malaysia using PV watts calculator. And lastly, the formulas followed for the sizing of each of the PV system components. We will discuss the overall practicality later when we get to the results. So, in a recent experiment, the electrical consumption of the RTES was evaluated, and from this experiment, we were able to obtain the following details. The RTES uses 155.8 watt to function. It uses AC power, which means it requires an inverter. And lastly, the device includes a motor, which is a reactive load, which means that the inverter size will have to be the power multiplied by 3 to handle the initial surge. The vehicle considered is the same vehicle equipped with the RTAS for experimenting in the Vehicle Systems Engineering Lab. It is a light-duty vehicle as shown in the picture. We can get the required details about the vehicle from the specifications. So if there will be no additional frame installed, then the only available area is the area above the driver's seat, which is 1 meter long and 1.4 meters wide. The gross vehicle mass is 3,500 kilograms, and the battery on the vehicle is a 12-volt battery with a capacity of 80 ampere hours. To get an estimation for the daily solar irradiation in Malaysia, PV Watts calculator can be used. PV Watts is a popular web application that has a user-friendly interface to get an estimation for the solar irradiation and the potential power output from the solar panels. The data obtained are usually corrected according to the cell temperature. The graph shown is from a study comparing different PV energy evaluation software. The blue bar is the real data obtained directly from a real panel, and PV Watts is the green bar, and the values appear to be reliable to a great extent. To use the PV Watts calculator, we start by choosing the nearest grid cell to the target location on their website's database. Secondly, the system info needs to be added, and then results can be obtained, and it can be monthly data or hourly data for every day in the year. A PV system consists of a PV panel which converts sunlight energy into DC electricity, a solar charge controller to protect the battery by regulating the current and the voltage to avoid overcharging, the battery which stores the electrical energy and supplies it to the load, and an inverter to convert from DC to AC. The main reference for sizing the PV components is a study titled Design Considerations of Standalone Photovoltaic Systems. The table shows the formulas used for the sizing of each component. Now I move on to present the results. This graph shows the irradiance for each month in Malaysia throughout the day according to the data obtained from PV Watts calculator. Peak hours are the number of hours where irradiance is 1000 watt per square meter. The equivalent number of peak hours per day can be calculated by getting the total irradiation throughout the day and dividing it by 1000. With this calculation, we will find that Malaysia in general has an equivalent of 4 peak hours, but to gain the needed irradiation, the vehicle will have to be exposed to sunlight, particularly from 10 a.m. to 4 p.m. According to Waze, which is a navigation app commonly used in Malaysia, the average duration Malaysians spend on the road is 1 hour and 12 minutes. This is for urban driving, but we can also consider the number of hours spent in traveling distances from UTM KL to UTM JB, for example. According to Google Maps, this will take around 3 hours and 16 minutes. The sizes for the PV system components are listed in the table below. These were obtained using the formulas shown earlier. When comparing the two types of driving scenarios, we find that the main difference is the panel size and the days of autonomy for the same battery. This is mainly because driving hours in city are normally shorter. Another remark can be made by recalling the study made in Peru. There were drops in power caused by shades since it is an urban area. However, in the case of traveling, the roads do not have any buildings and there is no shading caused, and therefore the graph can be assumed to be similar to the orange line for the panel fixed on a building. In other words, the panels are less efficient in urban areas, but the driving duration is not long anyways, so the electrical requirement can still be achieved. Meanwhile, on traveling roads, more steady power output is required, and that is actually achieved since there is no drops caused by shades. An interesting experiment was made by Chris Fix, who has a large automotive DIY channel on YouTube. In the experiment, he was trying to figure out how much weight can he remove from a vehicle and how will this affect the vehicle's performance. The mass of the vehicle particularly makes a difference during acceleration. The vehicle's mass originally was 3,370 pounds. He was able to remove 430 pounds, and the acceleration from 0 to 60 miles per hour before removing any mass took 6.8 seconds, and it took 6 seconds after removing the 430 pounds. So removing 12.8% of the mass caused an 11.8 decrease in acceleration time. The vehicle in our case is 3,500 kilograms. Meanwhile, the PV system components are well below 50 kilograms in total, so it is less than 1.5 increase in mass, and it can be assumed that this increase in mass will not have a significant effect. The results show that by having the vehicle exposed to sunlight, particularly from 10 a.m. till 4 p.m., the panel can generate a considerable amount of electrical energy that is sufficient to support the RTAS in the common driving patterns. The vehicle's battery can be used, although it can be argued that using an external battery can be safer and would extend the days of autonomy. The added weight of the PV system compared to the weight of the vehicle is not so significant, and so overall the PV system can be considered as a viable option. For the recommendations, firstly, it is advised to conduct an on-road experiment. The initial plan for this project was to use the panels and experiment with the actual vehicle, but because of COVID-19 and the movement restrictions, there was no access to the equipment. The experiment should obtain data for the panel's power output in real life while fixed and on the road. The fuel consumption with and without the panels can also be observed. Second recommendation is trying the same methodology for different vehicles such as buses and trucks, which normally have a complete rooftop area that can be easily utilized. Third recommendation is trying the same methodology for different electrical loads such as air conditioners, as they are one of the most common and significant electrical loads. This is the list of the references in this presentation. These can also be found in the description. That's all for me. Thanks for listening.